So what formulas have you seen so far for entropy? What equations show up in that? Yeah, I think that is, does that work? Yeah, one way of writing it is that 1 over temperature is the derivative of entropy with respect to energy. And the U here is just the internal energy. And the S here is entropy. And then T is temperature, which has to be in Kelvin because we're dealing specifically with the temperature, not change in temperature. And yeah, delta S equals Q over T is probably going to be a more convenient way of writing it. And we can actually get that if you imagine multiplying both sides by du. And you can think of du as being a tiny change in energy, and ds as meaning a tiny change in entropy. So if you're changing the energy, how do you change the energy of the system? What do you have to do to the system to change its energy? Yeah, add work and heat. And it turns out that only heat really matters in the cases we're going to be looking at. Because if you do work, like let's say you've got a gas in a container with a piston. How would you do work to this gas? Yeah, you'd apply a force, specifically apply a force to what part of the container? Yeah, to the top, the piston here. You'd have to apply extra force to the piston as it moves some distance so as to push it in. So let's say you push the piston inwards to a new location, thus compressing the gas. You're doing work on this. Work enters the system. That's an increase in energy, so you'd expect it to be an increase in entropy. However, we've also limited the amount of space the gas has to move in. If you put limitations on how much space the gas can move in, what would you expect to happen to entropy? That there's more limitations on where it can be. Yeah, if there's less space available, we should expect a decrease in entropy. And this goes back to the formal definition of entropy as a measure of the number of microstates available. Specifically, logarithm of the number of microstates multiplied by Boltzmann's constant. Number of possible microstates are sometimes called the number of accessible microstates. If you have shrunk the amount of space the gas has to move around in, the particles can't move around in as many places. Not as many places for the particles to be would suggest fewer microstates and a lower entropy. So less space to move around in would mean less entropy. Adding energy to the system would mean more entropy. And it turns out that these effects cancel each other out. Doing work to the system, as long as you're talking about a gas in a container, doing work to the system doesn't actually change the entropy. Adding energy would increase the entropy, but changing the amount of space it has to work with involves another change in entropy that cancels it out. Likewise, if you pull the piston out, you're removing work from the system. That would suggest a decrease in entropy because you're lowering the total energy, but you're also allowing it to have more space for the particles to move around it. So you'd be decreasing entropy because you're removing energy from the system and increasing entropy because you're allowing more space for it to play with. And again, those effects cancel out. So work alone does not change the entropy of this gas. And that's specifically for this system with the gas and the container with the piston. In other systems, work can change the entropy. But in this context, the only way to change the entropy of the gas is by heat. So in this context, we can treat du as heat. Specifically, we should write that as, or we should think of that as a tiny bit of heat divided by the temperature that the gas is at when you apply that heat equals the tiny change in entropy. So we could write this as tiny bit of heat divided by the temperature equals tiny bit of change in entropy. And this dq should be interpreted as a tiny bit of heat added or removed to the system. And if the temperature is constant, then every bit of heat we add results in the same increase in entropy. So if the temperature is constant, formally what we're really doing here is integrating. We're applying an integral to both sides. If t is constant, that can be pulled out of the integral. An integral of dq, that's literally just adding up all the tiny bits of heat to get the total amount of heat added or removed. And then integral ds, that's the adding up all the tiny changes in entropy, is the total change in entropy. So if the temperature is constant, we can use this idea that the change in entropy is the heat added or removed divided by the temperature. But again, that only applies if the temperature is constant. Any questions on that so far? Hello, we are looking into some of the formulas for entropy. So far, we've looked at the idea that entropy is really just a measure of the number of microstates, specifically logarithm of the number of microstates times Boltzmann's constant. And also, to change the entropy of a gas, you have to apply heat. So applying heat to the gas, if you just add heat to the gas, you're giving it more energy and allowing it to have more ways that energy can be distributed. So adding heat increases the entropy. If you remove heat from the system, you now have less energy to deal with, and there are fewer ways the energy can be distributed. So that would mean less microstates and lower entropy. So if the temperature is constant, we can use this formula, that the change in entropy is heat divided by temperature if temperature is constant. And the reason for the divided by temperature, one way to think of this conceptually is that if you've got a very high temperature, adding a little bit of heat when the gas is already at a very high temperature has very little effect. Like let's say you add 50 joules of heat to a gas that's already at 10,000 Kelvin. You're not changing it very much. It's already got lots of thermal energy. But if you add the same 50 joules of heat to a gas that's at only like 20 Kelvin, that's a much larger change proportionally. You're causing a much bigger alteration to its behavior. So high temperature means the same change, the same amount of heat doesn't actually cause much change in entropy. Low temperature means the same amount of heat causes a large change in entropy because it's comparatively a much larger change. And what are some situations where temperature would be constant? How could you add heat to a system without changing its temperature? Yeah, if it's going through a phase change, for example. If you're adding heat to, let's say, a block of ice to make it melt, it's staying at the same temperature the whole time. So let's try that. Let's say you have a block of ice. Let's say you've got 5 kilograms of ice at temperature 0 degrees Celsius, and you want to melt it. We add heat to melt the whole thing. So we now have 5 kilograms of liquid water still at 0 degrees Celsius. In that case, since the temperature is not changing during this phase change, we can use this formula, heat over temperature. And how would we calculate how much heat it takes to melt the whole block of ice? What kind of energy are we changing here? Thermal energy would be if the temperature is changing. But in this case, we're not changing the temperature, we're just changing the phase, we're melting it. So what kind of energy is involved in that phase change? Yeah, this is just bond energy. If we were to draw out an energy interaction diagram here, we've got bond energy increasing because mass of the higher energy state, liquid, is increasing. It's an open system because we've got to add heat to make it happen. So our delta E, our conservation of energy equation will be delta E bond equals the heat added. In other words, the heat added is delta E bond. So we take delta E bond, because that's the amount of heat we're adding to make this melt, and divide that by the temperature. And how would we calculate delta E bond here? What's our usual formula for that? Yeah, M delta H, or formally delta M delta H, because we're talking about how much of the mass is changing phase, divided by the temperature because of the entropy formula. And how much mass is changing phase here? What's our delta M? Yeah, 5 kilograms. You could even think of that as final minus initial. The final mass of liquid is 5 kilograms because we end with 5 kilograms of liquid. The initial mass of liquid is 0 kilograms because we start with no liquid at all. So final minus initial, 5 kilograms minus 0 kilograms is 5 kilograms. And what about delta H? Anyone happen to remember the delta H for ice melting? Yeah, 333.5, I think that's it. 333.5, and that should be kilojoules per kilogram. And then we'll divide that whole thing by the temperature. And what is the temperature that this is happening at? Yeah, 0 degrees Celsius. So can I just take 5 times 333.5 divided by 0? That's not going to work, right? And what do I have to change the temperature to? Yeah, temperature has to be in Kelvin. If it's a delta temperature, Celsius and Kelvin are interchangeable. But if you just have temperature without a delta sign, it has to be in Kelvin. The reason for that is Kelvin, the number of kelvins actually means something. If we say like the temperature is 500 kelvins, that means actually 500 of something, 500 above absolute zero. But if we say the temperature is like 30 degrees Celsius, that doesn't mean there's 30 of something. It just means 30 marks higher than an arbitrary reference point, specifically 30 away from the freezing point of water. But the freezing point of water isn't some important universal constant. It's just a property of that one substance. So instead of writing this as 0 degrees Celsius, we should write it as 273 kelvins. And then we'll play all that out. 5 times 333.5 divided by 273. And I'm getting about positive 6.1. And then the units here would be kilojoules per Kelvin, because kilograms cancels out. So that would be the change in entropy. It's positive, meaning entropy is increasing during this process. You add heat, melt the ice, you're causing the entropy to increase. So the liquid water is at a higher entropy than the solid ice was. And these are the usual units for entropy, joules per Kelvin or kilojoules per Kelvin or something joules per Kelvin, whatever the prefix happens to be. But it's an energy over a temperature, so it's something joules over kelvins. Any questions on that so far? And if the temperature is changing, because this only works if the temperature is not changing at all. If the temperature is changing, sometimes we can still use this formula anyway. Like, let's say we take that liquid water. So we've got our liquid water, 5 kilograms at 0 degrees Celsius. And let's say we add some heat. And we now have the same 5 kilograms of liquid water, but it's now at a temperature of, let's say, 10 degrees Celsius. If we wanted to calculate how much heat that would take, what would we do? What type of energy are we changing here? Yeah, this is now a change in thermal energy because we are changing the temperature. So we can use, in this case, we have the mass, we know what substance it is. So what would probably be the most useful formula for delta E thermal here? Yeah, I would use MC delta T here. Which formula for thermal energy you want to use, because there's a lot of them, really depends on what information you know. In this case, we know the mass, so we've got M. We know the material, so we can look up specific heat of that material, and we know the change in temperature. So we've got mass. Specific heat of liquid water is that the 4.183, I think? Does that sound right? I should probably look these up to be sure. Liquid water, yeah, 4.18. And that's kilojoules per kilogram Kelvin. And then what about change in temperature? Do I need to convert these to kelvins first? No, I don't need to convert them to Kelvin. As long as you're talking about a delta, it'll be the same change, whether it's in Celsius or Kelvin, as long as you're consistent about it. For instance, final minus initial, 10 degrees minus 0 degrees is plus 10. Whereas if I converted them to kelvins first, we'd have 283 and 273. Subtract those, 283 Kelvin minus 273 Kelvin, the difference is still 10. So if you're talking about a difference, Celsius and Kelvin are interchangeable, as long as you're consistent about it. So I'm going to call the change plus 10 kelvins. That way, kelvins and kelvins cancel out. Also, kilograms and kilograms cancel out. We're left with 5 times 41, so 5 times 42 is 210. About 210 kilojoules. So that's the amount of heat it takes to warm this up. Is that wrong? 209. Yeah, 209. So it takes 209 kilojoules to warm up the liquid water. If we want to find a change in entropy, we've got the heat, 209 kilojoules. What temperature would we be dividing by? Should we be dividing by the 273 or the 283 or something else? And why is that? How would we decide? Like, is it at 273 the whole time? Or is it at 283 the whole time? Or what? Or is it somewhere in between? It's in between, right? If we use 273 as temperature, then we're assuming the temperature is at its coldest the whole time. So we'll get a lot of error in one particular direction. If we use 283, we're treating it as the hottest the whole time, but it's not. This is the hottest it gets. Most of the time it's colder than that. So we'll get a lot of error in the other direction. So if 273 is lower than it is the whole time and 283 is higher than it is the whole time, what would be a better temperature to use to be a good representative of the whole interval? What's a third temperature, somewhere in between, that's a better example of a typical temperature during this process? Yeah, we can take the average. If you take the average of the initial and final temperatures, that gives you a more typical in-between value. So average of 273 and 283 would be halfway between. That'll just be 278, because that's 5 above the lowest and 5 below the highest. So if we use the average temperature, this won't actually be exact, but it will give us a very close approximation. You can use delta entropy is approximately heat over the average temperature if temperature is changing a little bit. If the temperature changes a lot, like hundreds of degrees, then this is going to be way off. But for small changes in temperature, and 10 Kelvin is a pretty small change, then heat over the average temperature is going to be pretty close. So we can say delta S will be approximately 209 kilojoules divided by the average temperature, halfway between, which would be 278. So let's see what that looks like. 209 divided by 278 is about 0.751799 kilojoules per Kelvin. And I'm writing this out with so many extra decimal places because I want to see how this compares to another way of calculating it that's actually going to be more accurate. So it's a good idea to check how much more accurate. So this would be our approximation for delta entropy. It's not going to be exact because the temperature isn't 278 the whole time, but 278 is a good representative approximation because it's the average of the highest and lowest temperatures involved. Any questions on that so far? Then let's see if we can get even more accuracy. Because this is assuming that the temperature is not changing, but the temperature is changing. Let's go back to that previous idea that the change in entropy is the change in the tiny bit of extra heat divided by the temperature. If we split this up into a bunch of little tiny pieces, little tiny bit of change in entropy is caused by a little bit of heat divided by the temperature. But to add up all those pieces, how do you add up a bunch of little tiny pieces in calculus notation? What's the calculus symbol for adding up lots of little bits? That you usually see with D something? Yeah, an integral sign. In fact, what the integral sign actually means, did your calculus instructors ever actually show you what this sign actually means? What does that look like? What letter is that? That's just an S. It's a stylized S because it stands for summation. An integral sign is literally just talking about adding together all the little bits. Integral ds means you're adding up all the little tiny bits of entropy change. So the total of that, the total of adding up all the little bits of entropy change is just the total change in entropy. Adding up all the little tiny changes in entropy is the total change in entropy. For this one, integral dq over t, it's a little more complicated because t is not a constant. If t was a constant, we could pull it out of the integral and we just get 1 over t times the total heat, which is what we have here. But since temperature is not constant, we've got to be more careful. Instead, we can say delta entropy is the integral of tiny bit of heat dq over the temperature. But since we're talking about the thermal energy, heat is just delta E thermal, which is MC delta T. Or more generally, let's group together MC as heat capacity, capital C. So dQ, that's just the tiny change in thermal energy. We can write that as heat capacity times the change in temperature. But since we're talking about a tiny change in temperature, I'm going to write that as dT. So the heat is heat capacity times change in temperature. And then we're dividing that by temperature because delta entropy is heat over temperature. But heat capacity is constant. So what can we do with this constant heat capacity? What can you do with a constant multiplier inside a logarithm or inside an integral? Yeah, that constant multiplier can be pulled out as a multiplier. So we're left with heat capacity as a constant times integral of 1 over T dt. Like that. And do you remember from calculus what the integral of 1 over T dt is? Yeah, that is logarithm. So we end up with heat capacity times logarithm of temperature because of the 1 over T in the integral. And of course, we need to evaluate that from initial temperature to final temperature. Because this really should be a definitive integral. We're going from some initial temperature to some final temperature. So we should plug in initial and final and subtract. So let's see what that gives us. If we have delta entropy equals heat capacity times logarithm of final temperature minus logarithm of initial temperature, and these both have the heat capacity multiplier, but I'm just going to factor that out. So we've got heat capacity times final logarithm of temperature minus initial logarithm of temperature from the definite integral. But what can you do with logarithms that are being subtracted? If you've got a logarithm minus a logarithm, how would you combine those? Yeah, you can combine those logarithms by dividing what's inside. So delta entropy is heat capacity times logarithm of this divided by this, T final divided by T initial. So we can use this to calculate the exact change in entropy if the temperature is changing. Q over T average gives you a good approximation for small changes in temperature. But we now have an exact formula for the actual change in entropy if the temperature is changing. Delta S exactly equals the heat capacity of the object times the logarithm of the ratio of final temperature over initial temperature. So anytime the temperature is changing, you can use this formula. If the temperature is changing a little bit, this gives you a good approximation. This will be exact. Any questions on those formulas so far? So let's try using this one, because we got an approximation for the entropy associated with warming up this water. Let's use this formula to get the exact value so we can compare. We can say that the delta entropy is exactly equal to heat capacity times logarithm of T final over T initial. How would we calculate the heat capacity of this blob of water? We kind of already did this, right? In our previous calculation for heat, what part of this was the heat capacity? Yeah, specifically, well, 4.18 was the specific heat, and yeah, multiply that by the mass. Mass times specific heat is heat capacity. So heat capacity is mass times specific heat. And we can multiply those, 5 times 4.18. Same ones we had earlier. 5 times 4.18. And the kilograms cancel out, so we're left with just kilojoules per kilogram. Sorry, kilojoules per Kelvin. Times logarithm of final temperature, and these do need to be in Kelvin because it's an amount, not a change. 283 divided by 273. So 5 times 4.18, that'll be the heat capacity. So that's 20.9. And then multiply that by logarithm of 283 over 273. Natural log 283 divided by 273. The kelvins and kelvins cancel out. And I'm getting 0.75188 kilojoules per Kelvin. So the entropy is increasing by this much. So that's the exact amount, well, rounded off at the last decimal point. How does that compare to our approximation? It's very close. Yeah, we could have rounded this off to the third decimal point here, the thousandths place, and we wouldn't even notice a difference. You only get a difference in the 10,000th place, and even that is pretty darn close. So the approximation, heat over average temperature, gives you a very close approximation if you're talking about small changes in temperature. If we had been dealing with a very large change in temperature, then this wouldn't really be very accurate. But 10 degrees Celsius of change, that's almost nothing. So in general, the logarithm formula gives you the exact amount of entropy change if the temperature is changing. But if the temperature is changing by, I don't know, less than 100 degrees or something, Q over T average is usually a little bit faster and will get you a very close approximation. Ultimately, which one to use depends on how much accuracy you need. But for very large changes in temperature, you would definitely use the logarithm formula. Any other questions on those so far? All right, let's try out another example then. Let me include these as well, because I think we're going to the extra space. Let's say you have a cloud of steam. Let's say 3 kilograms of steam at, let's say 200, I'll say 500 degrees Celsius. And we put that we spray this steam into a very large room full of air. Lots of air at, let's say, 30 degrees Celsius. And we allow it to come to equilibrium. First of all, what would you expect to happen to the steam if there's lots and lots and lots of air? What would you expect the final equilibrium to look like? Yeah, if there's lots and lots and lots of air, the air is not going to heat up significantly. So we would expect all the H2O to come down to 30 degrees. So the final situation, in order for the steam to drop all the way down to 30 degrees, it's going to have to condense first. So the steam is going to condense. We'll end up with liquid water, all liquid water at a final temperature of 30 degrees Celsius. And the air hasn't changed. Air does not significantly change. The air is certainly absorbing all this excess heat, but we're assuming that that's not enough heat to change the air significantly because there's so much air involved. Realistically, it's going to warm up a little bit, but not very much. So we could use this information to figure out all the relevant changes in entropy. We could figure out how much entropy changes in the steam, and also even how much entropy changes in the air. And to do this, we're going to have to split this up into several sub-processes, because getting from steam at 500 to liquid water at 30 is several steps. First thing that happens to the steam is going to be what type of energy change. It can't change bond energy yet, though, because what temperature is it at? Yeah, first it's going to be thermal energy. It starts off way hotter than 100, way hotter than its condensation point. So it's going to have to cool off from 500 to 100 first. So the steam is cooling. So the steam cools off. That's going to be a heat equals delta E thermal. And then after that, the steam, the now cold steam, or relatively cold, 100 degrees, is going to condense. The steam condenses, it turns into a liquid. So that's going to be a change in bond energy. That leaves us with liquid water at 100, which then needs to cool off down to 30. So there's really three parts to this process here. The water cooling. So that'll be another delta E thermal. But since it's in a different phase, it's going to use a different specific heat. Specific heat of liquid water and specific heat of steam are not the same. So that means those are going to involve different values in the formulas. If we wanted to calculate each one of these individually, though, we've got our usual MC delta T. So that's mass, 3 kilograms. And then specific heat of steam, let me look that up. Steam is only 1.87, or 1.87 kilojoules per kilogram Kelvin. And what's the change in temperature here? We're assuming the steam drops from 500 down to what? Yeah, from 500 to 100. So delta T would be negative 400. And since it's a change, we can think of that as negative 400 Kelvin. So multiply that out. 3 times 1.87 times negative 400 is negative 2,244 kilojoules. So that's the heat required, the amount of heat that the steam has to lose in order to cool down to 100. How do we now figure out the change in entropy that is associated with that change? Can we just divide that by a temperature? Let's try that. Delta S is approximately heat over T average. So that's negative 2244 divided by, and then what's the average temperature during this process? If it's going from 500 to 100, what's halfway between those? Yeah, 300, although that's in Celsius. So how do we convert that to Kelvin? Yeah, and 273, so that's really 573 Kelvin. So negative 2244 divided by 573 is about negative 3.916 kilojoules per Kelvin. But note that that's just an approximation because the temperature is changing. If we want the exact value, we should be using the logarithm formula. So let's try that as well and see how they compare. delta S should equal exactly heat capacity times logarithm of the ratio of temperatures, T final over T initial. Heat capacity is still mass times specific heat. So that's the 3 times 1.87, 5.61 kilojoules per Kelvin. And then for temperatures, we just need to convert 500 and 100 to Kelvin. So add 273 to both. We got 773 divided by 373. Kelvins cancel out anyway, so we don't need to worry about the units there. 5.61 times logarithm of 773 over 373. And we're getting delta S is, wait, I got those mixed up. Final is 373, initial is 773. And that matters because logarithm of a number less than 1 is going to be a negative result, which we should expect. We should expect a negative value here. And I'm getting about negative 4.088 kilojoules per Kelvin. So now these formulas, at this large temperature change, these formulas do give us rather different results. Which one should we trust? Sorry, which one? Oh, the orange one? Yeah. This one was using the exact formula. The other one was using the approximation formula, heat over average temperature, which is, notice that this is still fairly close. It's only off by 0.1 kilojoules per Kelvin approximately. Maybe a little more than that, 0.17. But still pretty close, even though we're changing temperature by 400 Kelvin. But we should use the one from the logarithm formula because that's actually going to be the exact value. So that's the change in entropy. This steam is losing entropy. Its entropy is decreasing as it cools off. In fact, all of these are going to end up being decreases in entropy. For this one, we could actually use delta S equals Q over T because the condensation, the phase change, happens at a constant temperature. So you can calculate Q as delta M delta H. It'll be a negative value because we're losing gas. What was that? Oh, okay. For the condensation, we are losing entropy because the heat is leaving the system. So we're losing energy. And likewise, for the water cooling off, we would also have a decrease in entropy because energy is leaving the system. So we could add all those changes together, all the delta S's, to get the total change in entropy of the steam, the H2O. And that's going to be a very large decrease. Over time, this steam is losing entropy. Its entropy is decreasing. But the laws of thermodynamics suggest that entropy overall should increase. So how is it possible that the steam is losing entropy as time passes? Is the steam on its own a closed system? No. What else is it interacting with? The air. So if we're talking about the laws of thermodynamics, specifically the second law of thermodynamics says total entropy does not decrease in a closed system. To count as a closed system, we need to include the air. So the water, the steam, is losing entropy quite a bit, but the air is going to be gaining even more entropy as a result, because all the heat that the steam loses, the air gains all that heat. So for the air, you could take delta entropy equals the heat over the temperature. The air is gaining all the heat that the water loses. So all that heat as a positive, because the air is gaining entropy, gaining heat, divided by the temperature, 303 Kelvin, that'll tell you the change in entropy for the air. And if you calculate all of these, you'll find that the steam is losing some amount of entropy. The air is gaining even more entropy. So the total entropy of the entire system increases as a result of this interaction. Any other questions on that? You're welcome. So try running the rest of these calculations yourself. Try finishing off this calculation. How much heat does the steam lose as it condenses, and what's the change in entropy? How much heat does the now liquid water lose as it cools all the way to 30 degrees, and what's the change in entropy for that. Figure out all those heats and changes in entropy, add all the heats together to figure out how much heat the air is gaining as a positive, and calculate the delta entropy for the air as well. Compare those, that'll get you some extra practice, and you can verify that the second law of thermodynamics really does apply, that the total change in entropy should be a positive, or at least shouldn't be negative. It might be 0, but in this case, it should be positive, I'm pretty sure. So give that a try, get some more practice. Let me know if you have any other questions, and I will see you next time. You're welcome.